Hello students, so in this lecture we'll talk about interpolations. Now, quite often a function may be represented as a table of values instead of closed form expressions. For example, if we have a function like x and fx, that means for corresponding values of x, that is x1, x2, x3, and so on. We have fx1, fx2, fx3, and so on. Now, if the value of fx is to be found at some point in the interval x1 and xn, say, and y is not one of the tabulated points. That means, suppose there is a point y in between these values of x which is not tabulated, and we would like to find the value of that function, and it is y is in between x1 and y1. Then we would require the help of the interpolation technique. Now, if y is outside the interval, now if y is inside x1 and x1, then it's called an interpolation. And if y is outside, if y is outside this interval x1 and xn, then it is called an extrapolation. Now, the primary reason for this is the use of tables of values in a function like sine in a table and manual computation. In using computers, on the other hand, it is expensive to store tabulated functions in its memory. It is more convenient to use an algorithm to calculate the value of functions like sine or any arbitrary value of arguments. And that is how this interpolation becomes relevant. And another reason why the popularity of this interpolation is the theoretical foundation it provides for the derivation of differentiation and integration formula. So we'll take up one by one these interpolation techniques. We'll first start with something called Lagrange's interpolation. Now, this Lagrange interpolation, the universal technique for interpolation is to fit a polynomial through a points. Now, this polynomial is an approximation of the function. So we'll first start with polynomial. It's an approximation of the function. For example, let us take the example of this hyperbolic cosines. Suppose the following values are given, like for x and cos hyperbolic x, we have 0.1, and the value of cos hx is 1.005. Then for 0.2 we have 1.020. Then for 0.3 we have 1.045, and then 0.4 we have 1.081. Now the simplest polynomial is a straight one. So if we consider a straight line, the simplest polynomial, then the function is fx is equal to a1 plus a2x. So if we use the values at x is equal to x1 and x2, x is equal to x1 and x is equal to x2, these two values, then we come up with two equations. First one is fx1, which is equal to cos hx1, and it is equal to cos h, and x1 is nothing but 0.1, and according to this equation, and the value it is equal to a1 plus a2x, and this from the diagram, this from the table, we know that it is equal to 1.005. Similarly, for the second case, for x is equal to x2, we can write fx2 is equal to cos hx2, which is equal to cos h. Then the second value of x2 is 0.2, and it is equal to a1 plus a2 x2, and this is equal to 1.020. So these two equations of x1 and x2 are solved, and what we obtain is we obtain the value of a2 as equal to fx2 minus x1 divided by x2 minus x1, and we get the value of a1 as equal to fx1 minus x1 into a2. So at last we get, finally we get the following values of a1 and a2. We get the value of a2 as equal to 0.15, and the value of a1 as equal to 0.99, and suppose we would like to find out the value of value of fx, where x is equal to 0.16. So in that case we can use this relation, you can use the value. So we can write cos hyperbolic 0.16. It should be equal to a2, that is a1, that is 0.99, plus a2, that is 0.15 into 0.16, and the value comes out to be equal to 1.014. Now the true value of cos h 0.16 is equal to 1.0128, and what we obtained from interpolation is 0.014. Also, these two values are quite close. Now this was using the straight line. So use the straight line, that is fx is equal to a1 plus a2x, and this is called the first degree of approximation. Now when we use a higher order polynomial, so that becomes the second degree of approximation. So if one uses second degree of approximation, so in this case a higher order polynomial is used, that is fx is equal to a1 plus a2x plus a3x squared. Now our main objective is to find the values of these quantities, these coefficients, that is a1, a2 and a3, and to find out these coefficients we use the simultaneous equations as used previously. So we will have fx1 is equal to cos hx1, and it is equal to a1 plus a2 x1 plus a3 x1 square. The second equation is cos x2, cos hyperbolic x2 is equal to a1 plus a2 x2 plus a3 x2 square, and the last one fx3 is equal to cos hx3, and it is again equal to a1 plus a2x3 plus a3x3 square. So these three equations we will get, and now the form of interpolation polynomial chosen here is not actually convenient for is calculating a1, a2 and a3. The following assumed form of the polynomial leads to a triangular form of simultaneous equations. So what we get is we used better version, a more modified version. In that case, we'll, instead of using A1, A2 and A3, we will use this equation, that is fx is equal to b1 plus b2 x minus x1 plus b3 x minus x1 into x minus x2. So now our objective is to find the coefficients b1, b2 and b3. So we'll use the simultaneous equations, that is we'll use cos hx1 is equal to fx1 and by solving it found it comes out to be equal to b1 cos hx2 which is equal to fx2. This value is b1 plus b2 x2 minus x1, and the last one, that is cos h x3, its value is equal to the whole thing, that is b1 plus b2 x2 minus x1 plus b3 x3 minus x1 and x1 minus x2. So from the above equations we ultimately get the following relation, that is we get b1 which is equal to fx1, we get the value of b2 as equal to fx2 minus fx1 divided by x2 minus x1. This is similar to a1 and a2 values. The only difference is the value of b3 which is equal to fx3 minus fx2 divided by x3 minus x2 into x3 minus x1 and this minus fx2 minus fx1 divided by x2 minus x1 into x3 minus x1. Now this value, this quantity fx2 minus x1 divided by x2 minus x1, this is nothing but b2. So we can write this expression of b3 as equal to fx3 minus fx2 divided by x3 minus x2 into x3 minus x1 minus b divided by b2 divided by x2 this is x3 x2 minus x1. So if we substitute the values in the current problem, we get the value of b1 as equal to 1.005. We get the value of b2 as equal to 0.15. This is similar to the values of a1 and a2. obtained previously, and the value of b3 is 0.5. So again, if we use these values, we get the value of cos h 0.16 as equal to b1, that is 1.005, plus b2, that is 0.15 into x, value of x, that is 0.16, and lastly b3, that is 0.5 into x minus x1, that is 0.16 minus 0.1 into 0.16 minus 0.2. So this is nothing but equal to 0.06, and this is equal to 0.04. So ultimately the value of cos hx, it turns out to equal to 1.0128, which is exactly the value. It is correct up to 4 decimal places. So a higher order polynomial leads to a better accuracy. So higher order or higher degree, or its higher degree polynomial leads to better accuracy.